Welcome back, Physical Science 20. This is part 2 of the 1.3 video. So we looked at constructive and destructive interference with one-dimensional waves is what we refer to them as. Now we'll look at two-dimensional waves, i.e. ones that occur in water. Two rocks are thrown in a pond simultaneously. Two sets of circular waves that move outward interfere with each other as shown in the diagram. So over here in your picture you have like a rock thrown here or a rock thrown here, and the waves expand out. And what we'll have here is interference as well. Now, if you look at where we can see the circles, we'll assume the circles are crests. So crests, crests, crests. And kind of in between crests, we have troughs. And I'll just simply write in between crests. Okay, so what we'll see is that we have constructive interference where a crest of one wave meets a crest of another wave. We'll have constructive interference. And where we have a crest meeting it, so remember, crest meeting crest, we'll have constructive interference. Or where I have trough meeting a trough, I'll have constructive interference because they're making a bigger wave overall. But where I have a crest meeting a trough, there'll be a cancellation there, right? Destructive. So if you look at this diagram here, where I have a crest kind of in between, I'll have a destructive interference happening. So constructive, where crest meets crest, those are easy to see because it's where the lines overlap, right? Lines overlap, lines overlap, lines overlap. Constructive interference. But where I have a solid line in between two solid lines, that's where a crest is technically meeting a trough. Now later on I kind of redraw these showing dotted lines in between here to represent troughs. But for now, all we need to look at is just simply that there's interference with water waves. Where crest meets crest, we have constructive. Where crest meets trough, we have destructive. And of course, where trough meets trough, we have constructive as well. In some areas of overlap, crests of one wave repeatedly meet crests of another wave, as in figure B above. Constructive interference is occurring at these points, and the water continuously oscillates up and down with greater amplitude, of course, because constructive means we're making a greater amplitude, whether there are two crests or two troughs. In other areas, destructive interference occurs when the water wave does not move up or down. And we'll see in diagrams and in the simulation that it's a cancellation area. So where the crest meets a trough, we have that happening. For any two such waves, we use the term phase to describe the relative positions of crests. When crests and troughs are aligned for constructive interference, the two waves we say are in phase. So where a crest meets a crest, or where a trough meets a trough. At points where destructive interference occurs, crests of one wave meet troughs of another, so those are out of phase, 180 degrees out of phase, because we have a crest meeting a trough. That is, if the crests of one wave occur 1/2 wavelength behind the crest of another wave, the relative phases of the two water waves in most areas is intermediate between these two extremes, resulting in partial destructive interference. So we're kind of looking at the two different areas here where constructive and destructive happen, and then in between there, of course, we could have a little bit of destructive or a little bit of constructive. So looking at diffraction, waves spread as they travel. When two-dimensional waves encounter an obstacle, they bend around it and go and pass into the region behind it, as shown in the figure on the top page. This is called diffraction. So diffraction, we'll highlight that. Bending around a corner, if you will. That's what we're looking at. So if you look at this page here, what we have happening here, and again, we're going to go through this in the simulation here very soon. We have waves, so water waves here coming down. They're straight waves. And as we can see, they're bending around the corner. It's not just simply this. You just don't simply have waves going through because, oh, we can't bend around. There is bending around. So you can see bending around. Over here, there's an obstacle here. The waves are kind of coming down at an angle. And again, you can see there's a slight bending around that corner. The amount of diffraction depends upon the wavelength of the wave and on the size of the obstacle, as shown in the figure. So we can have waterways passing through grass, a stick in the water, a log, etc. Now, here's the key thing to know. We're going to put a star right here. If the wavelength is larger than the object, as with the grass blade, the wave bends almost entirely around. If it was a larger object, though, it wouldn't bend, and we would see kind of a cancellation area there. We wouldn't have a lot of waves going around. So that's what this part is talking about. As rule of thumb, only if the wavelength is smaller than the size of object there'll be a shadow. So what that means is indicating little bending. So if it's a really small wavelength, and by wavelength, of course, what I mean here is if we assume these lines are crests, so the distance from crest to crest is a wavelength. So in this case, you can see that this wavelength here, this distance, and if I look at this, what we'll see at the bottom, slit width, how wide the slit width is, you can see that this distance is bigger than wavelength distance. Therefore, we just have a little bending. We'll see at the bottom of the page, and with the simulation, that if this wavelength is bigger than the slit width, we'll have much more bending around the corner. So let's take a look down here. So if you look here, here's the wavelength here, so the distance between crests, and here we have the slit width. You can see this slit width and the wavelength are very close to being the same size. So this would be considered a large wavelength compared to slit width, and look at how much bending we have. It's almost all the way around, except over here there'd be a shadow region because the crests don't quite reach there. But if I make the slit width bigger, keeping the wavelength the same, so the wavelength is only this wide, but the slit width is this wide, so the wavelength is smaller, we have little bending. So let's just make a note around here. Wavelength slightly larger than slit width results in large diffraction. So that'll be for that diagram. So wavelength slightly larger than slit width results in large diffraction. Whereas over here, small wavelength compared to slit width results in small diffraction. Of course, by diffraction, I mean bending around the corner. So less bending. So only slightly curving around the edge, whereas here, major curving around the edge. All right? That waves can bend around obstacles and thus carry energy to areas behind the obstacle is very different from energy carried by material particles. Okay, so that's the basic rule of thumb there. Over here, of course, we have a similar thing. This object is really wide compared to wavelength. So again, there's little bending. If this object had been, this object is kind of behaving like a slit here. So if it was a smaller object, we would have way more bending. Okay, what we'll do is we'll stop there, and in the next video we'll look at a simulation involving some of this. Okay, we'll see you again.